Great. So today we're going to look at section 3.4, okay, which is on a different way you can do long division. I showed you guys a method yesterday that works all of the time. The method I'm going to show you today that's a little bit quicker is synthetic division, but the disadvantage is that synthetic division doesn't work all the time. So I put on the board that when you're finding the roots to an equation, sometimes you have rational roots, sometimes you have irrational roots. Can anybody tell me what it means if a number is rational? It could be a whole number, but it doesn't have to be. Whole numbers are rational, but rational numbers don't always have to be whole numbers, if that makes sense. It's kind of like saying, if you live in Massachusetts, you automatically live in the United States. Yep, that's true. If you live in the United States, you automatically live in Massachusetts. No. So you can say it one way, but not the other. Anyone else have an idea what it means to be rational? You can write the number as a...
You could just write it out, and you wouldn't have to keep writing number after number when we continuing.
Okay, so sometime it ends. Is that what you're saying? Like it doesn't go on forever? Yep. Some rational numbers stop. Some of them go on forever, like 0.3 repeating, but it's still rational.
It can be written as a fraction?
You can write it as a fraction. Okay, that's the key. So sometimes when you're finding roots, like the one we did right here, okay, or the one that was a little bit further to the left. I think when we looked at that one, it was like negative 0.002. And then it had a bunch of numbers after it. So chances are you're not going to be able to write that as a fraction. That's why I said don't solve it with algebra. It's going to be a pain. So we solved it graphically. Okay. What I'm going to show you is a method for finding all the rational roots. Okay, this is called the rational root theorem. And I want you to think of this theorem as a starting point. Okay? That's what it is. It's a starting point to help you figure out something. By itself, it doesn't directly give you the answer. You have to use your graphing calculator to go a little further. Okay, but this is a starting point. Okay, so suppose we had some polynomial. When we actually do a problem, it'll be something like that. 10x to the fifth minus 3x squared plus x minus 6. Okay, but for now, I'm just representing that generically. Okay, so we have some polynomial. And what we're going to focus on is that and that. Okay, so if we were doing an actual problem, just to kind of show you what you'd focus on, you'd be focusing on the number 10 and the number negative 6. Or positive 6. It doesn't really matter. First of all, in order for this theorem to work, I have to make a couple assumptions. First, I'm going to assume that all the coefficients are rational. Okay, so you don't have any square roots. That would be irrational. You don't have pi, like the symbol pi in there anywhere. Okay, all the coefficients can be written as fractions. And the other important thing is that the first coefficient and the last coefficient can't be 0. Okay, this theorem doesn't work if either thing I circled in red was 0. And in the problem we're going to do, one is a 10, one is a 6. Okay, that's fine. Okay, no zeros there. Okay, so any question on what the two things I circled in red are not allowed to be? All right. So if you can find a rational root, okay, if you can find a number that's a root that can be written as a fraction, it's going to be written just like this, in the form p over q. And I'm going to show you how you figure out what p can be and how you figure out what q can be. And it's going to relate to the two numbers I circled up above. P has to be a factor of the constant. Can people still see what's on the left if I make that a little smaller? Okay. P is a factor of the constant. So if we were doing an actual problem, we would be looking at the -6, and we would be writing down all the factors of -6. Positive and -1, positive -2, positive -3, positive -6. Those are all the numbers that divide into 6 without remainder. Okay, so you'd write that list down. Q is all the factors of the leading coefficient. Okay, so if we were doing an actual problem, in this one it would be the number 10. And you'd write down every number that divides into 10 without remainder. Okay. And then the list that you're going to create is every possible value for P divided by every possible value for Q. Okay, so we have to somehow kind of make an organized list for doing that. Okay, and we'll go through and I'll show you how to do it. Not every single number in that list is going to be a 0. What this theorem does is it generates a list of possibilities, which we then use the graphing calculator to narrow down that list. Okay, so what we'll do is we'll use the theorem, we'll make a list of possibilities, then we'll take out the calculator and use the calculator to narrow down the list. All right, so let's, actually, let me make this page bigger again. Okay, does everybody have that paragraph? PQ. Okay, so just remember, and maybe off to the side or somewhere, you want to remember, P is a factor of the constant, so I just write it down so I remember, and Q is the leading coefficient. Okay, so let's make a list of all the rational zeros here. Okay, so let's start with P. P is all the factors of the constant. First of all, can someone just tell me which number am I focusing on? What number is the constant here? Josh?
The -6.
The -6. Can somebody give me a factor of 6? It would be a number that divides into 6 without remainder. Yeah, Nina? 3? And what about? All right, so 2 and 3, that would be like the family there. The 2 times 3 gives you 6. How about -2 and -3?
Yeah.
Yeah, so anytime you have a positive, the negative goes with it. Positive -2, positive -3. And so there's 4, but there's 4 more. AJ?
6 more.
And what else? 6 and 1? And -6, -1. Okay, so we've got our list for P ready. And now for Q. Q is a factor of the leading coefficient. Hannah, what's the leading coefficient here?
10.
10. Okay, and Mallory, can you give me a couple factors for 10?
1 and 10.
Sure. Could you do positive -1? Positive -10? Casey, can you give me the other two that go together?
2 and 5.
2 and 5. Now, if there is a rational root, in other words, if this graph crosses the x-axis, somewhere that's a fraction, it can be written just like that. So now we have to generate a list of possibilities, every possible P divided by every possible Q. Okay, and the way I do it, I'll show you. So this is a list of possible. Not saying that they are, I'm just saying it's a list of possibilities. Rational roots. Okay, I'm going to start with the first P, and I'm going to divide that by every Q. So I'm going to have positive or negative 1 divided by positive or negative 1. That's just 1. 1 divided by 2. Okay, that's the next one. And again, these can all be positive or negative, but I'm not going to say that every time. 1 over 5. 1 over 10. So those are all the different possibilities with 1 in the top. Now we'll go to the next one. Let's do all the possibilities with 2 in the top. Andrew, could you give me the first one you would do? It would be 2 divided by 1. Yep. You want to keep going and give me all the ones that you could do? With 1. Yep, the next one would be a repeat. 2 divided by 2. We already have that one, so you don't need to write it again. What would be that one? Next one?
2/5.
Yep. Positive or negative 2/5. And the last one?
5. Wait, oh no. 1/5.
Positive or negative 1/5, because it's 2/10, and do we already have that one? Yeah. 2/10 is 1/5. Okay, so you do get a lot of repeats as you do this. Hey, let's do the next one. With 3. How about Ezekiel? What would be my possibilities with 3 in the top?
Positive or negative 3.
Yep. What else?
Positive or negative 3 halves.
Positive or negative 3 halves.
Positive and negative 3/5.
3/5. I don't see any repeats so far, so that's good.
And positive and negative 3/10.
Positive or negative 3/10. And the last one, we'll do with 6 in the top. So 6 over 1. We've got 6 over 2, but do I already have 6 over 2?
Yes,
3, I just did that. 6/5, I don't have that one. How about 6 over 10? Yeah, 6 over 10 reduces to 3 over 5. We have that one. So, if this graph is going to cross the x-axis somewhere that's a fraction, I guarantee you it has to be one of those numbers. So we just generated a list of, what, 4, 6, 10, 11, 12, and double it for negatives. That's 24 different options. Those are the only 24 places this graph could cross the x-axis. That is a fraction. And that's it. So any questions on what we did there? Okay, so now we're gonna need that to do the next step, which is to take the same problem that we just had, and now we're going to show that that graph does cross the x-axis in one spot, but that it's an irrational number. That it crosses the x-axis in a spot you cannot write as a fraction. Okay, so now I'm going to use my calculator, and we're going to type in the problem. Okay, so we've got 10 x to the 5th minus 3x squared plus x minus 6. What would be a good zoom to start with? Because I know in the last problem when we did homework we had zoomed out to like 30,000, so I probably need to reset it.
Standard?
Yeah, just the standard zoom. Okay, make sure we have it typed in right. Looks good. Okay, so it's drawing it, it's thinking about it. There we go. Where does it look like it crosses? Let me make it a little bigger. Anybody see where it looks like it crosses the x-axis? 1, and I would say 1 is a reasonable guess. So now let's make a list of what I call candidates, okay? Using that picture. So the list of candidates is now we're going to take that list we have and we're going to narrow it down. I would say plus 1. Well, you don't even have to write the plus. Just 1 is a candidate. Would you say -1 is a good candidate? No, it doesn't even look like it gets anywhere close to -1. How about 1/2 or -1/2? Not really. It's not really close to that. Positive or -1/5? Positive or -1/10? No. How about plus or minus 2? No. -2 would be over here. Positive 2 would be over there. It doesn't look like it's anywhere close. Positive or -2/5. I don't really think any of these are candidates except maybe you could argue 6/5. Because if you divide 6 by 5, it's just a little bit bigger than 1. 1.2. Maybe if I zoomed in a little bit, that might be close to 1.2. But I would say 1 is probably your most reasonable guess. Okay, did anybody actually graph that and calculate what the root is? Did it come out to 1?
No.
No, it's not going to come out to 1. So let's do second calc. Second calc. Let's try again. Second. It's a little touchy sometimes. Second calc, let's do 0, because we're trying to see where it crosses. Pick a point to the left, make sure you hit enter. Pick a point to the right, and take a guess. So it looks like it was close to 1, but it actually wasn't. It was 0.951. Okay, that's where it crosses the x-axis. Okay. So right here, that's about 0.951. How come 0.951 has to be irrational? Because that's what the question was. It was to prove that it has one real root. Okay, we did that. You can see it crosses. But then the second part, show that it is irrational. Means it can't be written as a fraction. How come that can't be a rational root? Think about what we just did, yeah.
It's not on the list of possible.
This is the only list of possible rational numbers you could have. 0.951 is not in that list. Okay? So if you come up with a root, and it's a number that's not in the list of possible rationals, then the only other option, it's irrational. So we just discovered a number that's not in the list of rationals, that has to be irrational. Right? So just write that down. So since 0.951 is not, and I'm just going to reference our list of possible rational roots. So it's not in our list of possibilities. It must be irrational. So, any question on how we show that 0.591 is a root and how we concluded it has to be irrational? Okay, so as far as the rational root theorem, that's it. That's all I'm going to show you with that. Okay. Has anybody, maybe last year or in a different class, done synthetic division? Yeah, synthetic division is a lot nicer way to divide. It's a lot faster, but the disadvantage is it only works on certain kind of problems. If you're clever, you might figure out a way to tweak it a little bit and make it work on other problems, but I'm not going to show you how to do it. I'm just going to show you how to use it on the very basic problems. So you would have to have something like, let's see if I have an example, like this. You have to divide by something that's either x plus a number or x minus a number. If you make it like x squared or anything else more complicated than that, you've got to go back to the way we learned yesterday. As long as you divide by something that's x minus a number, I'll show you how to do it. And what I'll do is I'll do this similar to the way we did it yesterday. I'll kind of show you the steps. And as I do that, I'll do an example at the same time. All right, so we've mentioned a couple things that are similar, okay? Statements that mean the same thing. If 3/2 is a root, or if 3/2 is a 0, what else does that mean? It means it's an x-intercept, but I'm looking for the other one.
X minus that is a factor.
Right. So what I'm really going to show is I'm going to show that x minus 3/2 is a factor. Okay? And by showing x minus 3/2 is a factor, that indirectly proves 3/2 is a root. That's how you always do this kind of problem. Now, to show something is a factor, I do division, and I hope for a remainder of 0. Yeah. So that's what we're going to hope for. All right. So the first step, it's kind of similar to yesterday. Let me write down what we're doing. So we're going to divide that original by x minus 3/2. This is what I'm about to do. And if you do that and get a remainder of 0, then it's going to prove what they're asking for. Okay, so step 1 is to put the number that comes after the minus sign. Okay, I want to be very clear, you don't include the minus sign. Just what comes after. So put 3/2 on the outside. Now fill in all your coefficients. And put zeros for anything we're missing. Brandon, am I missing anything in my numerator for terms?
No.
No, I've got the cube, the squared, the linear, the constant. So 2, -5, what number is in front of x?
1.
Yep, 2, -5, 1, 3. Nice thing about synthetic division is I can basically put a box around that. All my work is going to fit in that box. Long division, you kind of get into that pattern where you're going like down and to the right, and it just keeps going kind of that way. Synthetic division, once you put your columns, it's a fixed amount of space. Okay, so not only is it faster, but it takes up less space on paper. Okay, so put C down, put down your coefficients, fill in any missing powers. We did that. Bring down the first coefficient. The first coefficient, 2. Just bring it down. Next step. Multiply the divisor, which is 3/2, by 2. And we're going to put the answer right there. Okay, I'm going to erase that x, but that's where the answer is going to go. Okay, so let's do that out. What's 3/2 times 2? Well, think of 3/2 as 1.5.
2.5.
So if you double 1.5, what do you get? 3. Yeah, sorry. Okay, so we get 3. We put the result in the second column, because that's what it's said to do. And now we're going to add those two numbers together. What's -5 plus 3?
8. Or -8. No,
Careful.
2. -2.
-2. You had every combination in there. So -5 plus 3 is -2. And now we repeat the process again. We keep repeating it until we're done. I'll explain when you're done, how do you interpret the bottom row, what that means. Okay, but I'll do that in a second. So just leave a little, you're probably going to need about one or two more sentences worth of space. How about Curtis? What's 3/2 times -2?
-6/2.
Yeah, -6/2. That's a good way to think about it. And what's -6 divided by 2?
-3.
Yep, -3. And now, Cameron, what do I do with the 1 and the -3?
You add them together.
Add them together. That's a big difference from long division. Long division, you subtract. This you add. What's 1 plus negative 3?
-2.
Negative 2. Now we do it one more time, and in fact, it's the same number we just did it with, so we're going to get the same result. Negative 2 times 3 halves is negative 3. Add them up, you get 0. Anyone have a guess what that 0 is?
Remainder.
Yep, that's the remainder. Okay, so if that's the remainder, then this part would be your what?
Quotient.
That's your quotient. Okay, so the last row contains the coefficients of the quotient and your remainder. Okay, so your quotient, if you were actually going to write out the answer, is that's your constant, that's your x term, that's your x squared term. Okay, so anyone think they could tell me how they would write that out? That's the quotient, yeah?
2x squared minus 2x minus 2.
Yep. So that's your quotient. Remainder, 0. Now, the other thing it said to do was to show that that was a root. Well, I showed x minus 3 halves as a factor because it had a remainder of 0, so I've done that. Now, they want us to factor it. 2x cubed minus 5x squared, that original problem. What do we already know is definitely a factor of that from what we just did?
The quotient that we had before.
Yes, the quotient. Remember we said if you divide two things, like if you take 12 and you divide by 4, the quotient, whatever the answer is to 12 divided by 4, that is a factor of 12. So, as Josh just said, the quotient is a factor. 2x squared minus 2x minus 2. But there's one other one. What's the other factor of that?
X minus 3 halves.
Yeah, x minus 3 halves, because we divided it in with a remainder of 0. That's the other factor. So if you were going to factor this problem, that is how you would do it. So in order for this method to work, I always have to give you at least one place that it crosses the x-axis. That's a nice number. The first problem I gave you, you wouldn't be able to factor it out. Any questions on that one? Why don't you guys take a second and try that one on your own. Use synthetic division to find the quotient and the remainder when you do that out. Now be careful. When I said you divide, you have to divide by something that's in what form? To use synthetic division.
Plus or minus, x plus or minus.
Yeah, I didn't say plus or minus. I said it had to be one of those. It had to be x minus c. Right? So if it has to be minus, how are you going to think about x plus 3? Right. Negative 3 is the number that's going to go on the outside. Okay, and I'll let you try the rest from there. So first thing you want to remember is you're missing which term?
The squared and just the squared.
Just the squared. So we got 3, 7, 0, that's important, and then 1, negative 11. Okay. Step 1, bring down your 3.
-9.
Now multiply negative 3 times 3, as Evan just said, negative 9.
-2.
7 plus negative 9, negative 2. Now do it again.
6.
Negative 3 times negative 2 is positive 6, so you're good.
6.
That gives you 6.
-18.
Negative 18.
17.
That was weird. Negative 17.
51.
51. And then plus negative 11.
Oh, it's negative 11?
Yeah, the last one was negative. So what does that mean about x plus 3? It's not a...
This would be
Okay, x plus 3.
Well, we divided and there was a remainder that wasn't 0.
So it's not a factor.
It's not a factor. So if you were trying to factor this problem, x plus 3 is not a factor. Okay, so it says write the quotient and remainder. Everything to the left of that line is your quotient. So we've got 3x cubed minus 2x squared plus 6x minus 17. What's the number to the right? Remainder. Okay, so there's your quotient and remainder. Okay, so synthetic division, we don't always use it. You can use long division if you want, but people tend to like synthetic because it's faster. Okay, so this one says show 3 is not a 0. Show that 3 is not a root. Well, what's another way to do that? If 3 is not a root, what is not a factor?
X minus 3.
X minus 3. So I'm going to show that x minus 3 is not a factor by doing synthetic division and hoping that I get a remainder that's not 1, not 0. If I get a non-zero remainder, then it's not a factor, which means that's not a root. Okay, what number would go on the outside here? Well, this is basically what you're doing.
Negative
Why that changes color like that, I don't know yet.
3.
I think it's because I get close and this camera picks up something else. I don't know.
3.
Yeah, 3. So 3 goes on the outside. What about my coefficients? Am I missing anything?
No.
Nope. Okay, first step. Bring down the 2. 3 times 2. Add that column. 11. Multiply again. What's 3 times 11? 33. Add that column. 31.
Wait, I thought you subtract.
No, add the column.
Oh, wait, yeah.
Well, you're adding a negative, so it's like subtracting this time. And then 3 times 31. 93. And then negative 3 plus 93. 90. What's my remainder there?
90.
Yep. Since I got a remainder of 90, that proves x minus 3 does not divide into the numerator, which also proves 3 is not a root. Okay, that's how you prove it. Any questions on that? Okay, so if they give you a problem and they say, find all the zeros, generally the strategy, kind of the order of things to do is what we learned. Start with the rational root theorem, make a list of possibilities. That first problem that I gave you to do rational roots on, that was a lot of possibilities. In fact, no problem that I give you for the rest of today or on the test will ever have as many possibilities as the first one. So make a list of possibilities. Use the calculator to narrow it down, that's graphing calculator, and then finish with synthetic division. Because once you find a root, then you want to divide through by it synthetically. Okay, so rational root theorem, graphing calculator, synthetic division. Okay, so let's start with the rational root theorem here. What number do I focus on for P? 2. What are the factors of 2? 2 and 1. That's it. So there's not going to be that many options. What's Q in this case? 1. It's right here. It's invisible. What are the factors of 1? 1 Well, 1 and 1, yes. 1 and negative 1, yeah. So now let's make a list of every possible p over q. There's only going to be 4 of them. Can somebody give me the list of possible rational roots? 1 and 2, and? So I agree, 1 over 1 is 1, 2 over 1 is 2. The negatives. So, when we graph this, if this graph is going to cross at a nice answer, it has to be either positive 1, negative 1, positive 2, or negative 2. The reason it's helpful to know that is because when I set my window, I don't even need to look from negative 10 to 10. Okay? All I need to focus on is between negative 2 and 2. I like to not have it right on the edge, so I'll do negative 5 to 5. And now type in the problem. So we get x cubed minus 3x minus 2. Now, once we see this picture, we're going to narrow that list down to what we think is good. Okay. Do any of these numbers look reasonable? Yep, I would say the negative 1 looks reasonable, and the positive 2, and they actually both are roots. So if you're like, well, which one should I divide through first by synthetically? It doesn't matter. Okay, we can do either one. So do we want to do the negative 1 or positive 2? Positive 2. Notice what kind of equation you have right now. It's a cubic. Keep that in mind. The degree is 3. Okay, let's divide through by 2. Am I missing anything before I fill it in?
Yeah, the square.
The squared. So what am I going to fill in?
0, that's great.
So 1, 0, negative 3, negative 2. Now, I told you, but you could also check. If you go to 2, y is 0. So the calculator just confirmed that it's a root. So when I do this division, what am I going to get for a remainder?
0.
Exactly, 0. Okay, so bring down our 1. 2 times 1 is 2. Add. 2 times 2 is 4. Add. 2 times 1 is 2. Negative 2 plus 2 is 0. And that's our remainder. What's this part again? It's the quotient, and that's the other factor. So now let's make a list of roots off to the side. 2 is a root. We just confirmed it with synthetic division. Now, focus on that part. How would you write this out? Yep.
X squared plus 2x plus 1.
So now you've factored out one of the roots, and what kind of equation do you have now?
Quadratic.
Quadratic. What kind of equation did I say to keep in mind that we started with? Cubic. So every time you divide through by a root, this exponent drops down 1. Okay. So we started with a cubic, now you're left with a quadratic. And that's a quadratic that factors. Did anybody see how that one factors?
What's 1? X plus 1.
X plus 1, x plus 1. So now set each factor equal to 0. And you're going to get the same answer twice. This is what we call a repeated root. And what's the repeated root? Negative 1. So if we're putting all our answers in the same spot, your roots are 2 and negative 1. And I might have mentioned yesterday that anytime you have a repeated root, the graph goes up, gets very close to the axis, just touches it, and then bounces away. Okay. Any question on that? All right. Let's just do one of these. Let's try this one. Okay. Let's find the rational zeros of this one. Okay, what degree is this equation? It's cubic. So if I can just find one root, I'm good. Then I can turn it into a quadratic. What are my possibilities for p this time? There's not really a lot. Plus or minus 1. Possibilities for q.
Plus or minus 6.
Plus or minus 6, yep.
1.
Plus or minus 1.
3.
3. And 2. So plus or minus 1, 2, 3, 6. So all my roots are p over q. What's 1 over 1? I'm not going to write the whole thing out, but this is our possible rational roots. 1. 1 over 2, how do we write that?
Plus or minus 1/2.
Just plus or minus a half. Plus or minus a third. And plus or minus 1/6. Okay. So let's, well actually you tell me, how do I narrow that list down? Graph it. Okay. Graph it. So we've got 6x cubed minus 5x squared plus 3x x minus 1. Now, I only need to look between, the biggest number in this list is 1. The smallest number in that list is -1. Right now, I'm looking between -5 and 5. That's okay. I'm looking further than I need to. Focus on what's in here. Okay. What? Let's take a guess. It's definitely not a negative. What does it look like? You can quickly check it just by trying trace. Yes, positive a half is a root. So let's finish up by dividing through by positive a half.
So you get, with the possibilities, you get p by going to the end of the problem, and that's like...
Yep. P, you use that number. Q, you use that.
Okay.
Okay. Coefficients, am I missing anything? Nope. Okay, so let's go through. Bring down the 6. What's half of 6? -5 plus 3? -2. Half of -2? Careful, -1. And then add again. Half of 2. Let's see. 6. 1, 2, 1. And we should get a remainder of 0, so I just copied a sign wrong. Yes. Simple fix. Make sure you copy your signs, right? 0. Okay. And now you're left with this. If you wanted, what could you factor out of all of those to make them a little smaller?
2.
Yeah, you could factor a 2 out. And if I did that right. And now, I'm not sure if this one is factorable, but if it wasn't, how would you solve 3x squared minus x plus 1? If it wasn't factorable. How else can you solve a quadratic besides factoring? Yeah, you could factor, if possible. Leave that to you to figure out if you could do it, or use the quadratic formula. Now, once you get all your answers, remember, they only wanted the answers you could write as a fraction. So if you use the quadratic formula and you end up with a square root in your answer, that's not one that they wanted. Okay? Does anybody know if they want all the answers, what would they say? They wouldn't say rational, they would say, what's the bigger category? Real. Yeah, real. Okay, so homework tonight it's on 183. Okay, so try those questions. Tomorrow we'll go over them first thing. We'll also finish everything for the week tomorrow, and then we'll have our test on Friday.